Hello and welcome to my presentation on our research project on design and fabrication of curved sandwich panels. I want to start with a short motivation on why we have done this research, look after that at the state of the art. Then I will show you the design tool we developed, the production process that was necessary to improve for this fabrication, and the research on the load-bearing capacity, because curved sandwich panels show much better load-bearing capacity than the flat panels we usually use. And I will finalize with a conclusion and an outlook. What is the motivation to work with curved sandwich panels? Straight sandwich panels, as we use them in millions of square meters every year, are a good value building product. They give very good heat insulation, they are water and airtight, and so they are a very well established product. We can build nice architectural design buildings, but we are restricted to plain and straight structures. They don't have to be square. You can also do something not as square as you can see on the left-hand lower picture. But in general, we are not able to build structures like this, large spanning or biaxially formed surfaces, roofs, for example, for large fairground halls or sports halls or something like this. One dome was built 50 years ago by Professor Otto Jungblut at the fairgrounds in Hanover. You see this large dome that was hand fabricated. The top and bottom plates are 1 millimeter, and in between is a polyurethane foam. But it's still standing after 50 years. That shows the long standing and long life capacity of sandwich panels. When we started with our product and our project, we had to look at the design tool, how we come from a general form to a single panel. And here we found out that there are 4 levels of complexity. Level number 1 is a uni-axially curved sandwich panel, so a panel with parallel edges. We have panels like this available on the market, but their upper surface is a trapezoidally formed surface. And that makes it difficult to make good joints that are air and watertight if you want to cut them with non-parallel edges, as you need it for a biaxially formed large roof, for example. For this you need flat surfaces. So level 2 of complexity is a uni-axially curved panel with non-parallel edges, and level 3 is the same with a twisted panel, as you see in figure 3. And the most problematic highest level of complexity is a biaxially curved panel with non-parallel edges, which we don't consider in our project. To develop a design tool, first of all, you need a curved surface. For example, here at the top left-hand picture, you see a structure 15 by 15 meters. It's kind of a bubble, and you cut this bubble into a number of slices. Like you peel an orange, you get tapered surfaces, and you can cut this, as you see in the second and third picture in the top row, and on the fourth side you see various singly curved surfaces that form, as you can see in the bottom picture, a biaxially curved panel or a singly curved panel, but you get a general surface that is biaxially curved. So what we do is, first of all, we need a surface, a roof like here a multi-band wave-like structure. So we analyze the load-bearing behavior. After that, we find a panel layout you see here in the central picture, and we detail and develop this with joint geometry to form a CAD model that's given for fabrication and for final design. In this picture you can see how 4 tapered stripes can form a final surface. Unfortunately that went too fast. Here you can see it in slow motion, how we have 4 tapered panels that form one final surface. So problem here is the joint. To form the joint, if we look at the next picture, here we see this area here, because in straight panels you have a straight joint that is formed L or form L-like, and you get a good airtight joint. But if you have a tapered and bent panel, this joint will move. It will have to be bent inside, upside down. So it's not a straight forming process. You need a special roll forming process for this, and that's shown in the next slide. First of all, we uncoil the plate, we cut it to this tapered form, as you see here in the second picture. Then with a flexible roll forming, the joint geometry is formed. And finally, with a plastic coated roll, it is bent. Currently we can bend it in a uniaxial curvature, but in future it might also be possible to bend it in a multi-axial curvature. With 2 plates, we can put these plates in a form work to hold them while the forming process is taking place. If we look at the load-bearing capacity, here you see a test on one of these sandwich panels that we fabricated in this way, and that showed very good load-bearing behavior. The advantage of an arch over a straight surface is that in an arch you have not only the load distribution by bending moment, but also by normal forces, and the steel surfaces that are supported by the foam carry these normal forces quite well. So we did a few tests, and after that we did some finite element modeling, and the finite element models and results were of course checked with a test to get a good correlation between them, and then we took a large number of parameters for a numerical study, thicknesses from 40 to 300 millimeters, span lengths from 2 to 30 meters, and curvatures from 0.5 to 32, which means a radius over the span length. Face sheets were 0.46 millimeters, and the core material was a typical polyurethane foam core material. The result was quite interesting. If we look here at the blue line that's given for the stress for symmetrical load depending on the span, the gray is for asymmetrical load, so only half of the span is loaded, and the red line here at approximately 90 some Newton per square millimeter is a wrinkling stress. So that's what the panel is able to bear. And here we have an example with a load of 1 kilonewtons per meter, which is approximately the snow load in Central Europe. And you see that especially in the area of a low curvature, say from 4 to 0.5, we are much better than the straight panels here or here, and in the high values, large values, we are not as good. And we see this here in this picture If you have a low curvature, you even get negative bending, you get a little bit positive, some more negative bending. And if you have a medium curvature, 1 to 2, you get no bending at all. All the loads are distributed by normal forces, which leads to very low stress. And the larger, the greater the curvature R over L gets, the more you come to a straight sandwich panel, and then you just have a positive bending with a normal load carrying behavior. We looked at some parameters and some setups with symmetric load and asymmetric load. Of course, snow has to be asymmetric, so we have to look mainly at the right-hand side of this figure. If you look just at symmetric loads, 16 meter span with a thickness of approximately 160 millimeters and a curvature smaller than 2 seems to be feasible. But for practical purposes, asymmetric load is mostly decisive, especially with snow or wind. And here we get up to 16 meters. We get 40% of the systems we checked were stable, but we need a thickness of 300 millimeters, so you cannot span this with very thin or shallow panels, and with a curvature of R over L of about 1. So to sum it up, the curved sandwich panels have a high structural potential compared to a straight single sandwich panel. We span up to 2.5 times as long distances as we do with a flat surface sandwich panel. We developed an automated design tool that is available for whoever is interested. We developed an interface between this design tool, the manufacturing process, and the static model to not only design but also to fabricate and to prove the resistance of the structure. And so we think that a high level of prefabrication can be achieved, which makes curved sandwich panels to a reasonably priced final project. And we showed that spans up to 16 meters are possible. That's a span that covers, for example, a normal Central European parking deck or a sports hall for schools. So there is, I think, quite a good market. And thank you very much for your attention.